Bons. I'm from the CWI, the Dutch National Research Institute for Mathematics and Computer Science. I'm going to talk about, give you an update on DuckPGQ. I'll tell you what DuckPGQ is. And this work is mostly the work of my PhD student, Daniel ten Wolde, who has put a lot of effort in DuckPGQ so far. And I will also report on two kind of recent ongoing projects by two master students who just finished, Pingan Ren and Paul Gross. I'm in a happy occasion because we're late towards lunch to be able to skip my first 12 slides because I had some information about what SQL PGQ is. So, well, that was exactly what Oscar has been talking about in the past 20, 30 minutes. So that's great. So we'll gain some time here. But I'm, of course, happy to spend more time on other things now. First of all, DuckDB, for those of you who may have been living under a stone, DuckDB is an analytical database engine that is so-called in process and has been gaining a lot of popularity. So in process means it's an embedded database system, and it's developed by my colleague Hannes Mueijsen at CWI, but currently also and mostly maybe the CEO of DuckDB Labs, which is a CWI spin-off company, and his first PhD student and postdoc, and now CTO of DuckDB Labs, Mark Raasveld, and you see their pictures here. So they developed DuckDB. The reason why they started working on DuckDB is that they realized that data scientists, and there are lots of them, there are millions of them actually, they truly hate database systems, they hate us, and they refuse to use database systems. They instead use pandas and Python, and they figured out, well, this is not too good because pandas actually doesn't have a query optimizer, doesn't have factorized query execution or JIT, or not even parallelism. It materializes everything, it breaks. So why are these people ignoring 40 years of database technology? So they try to work on DuckDB, and actually we at CWI, we have been working a lot on performance, and DuckDB is a kind of best of breed, and it has good performance. It's best of breed because it has all the things that CWI did in analytical databases, vector-wise and MongoDB, so column store and vectorized query processing, and it also has a lot of ideas from TOOM, so the Umbra and the Hyper systems, well, they did things like Morsel-driven fine-grained parallelism that self-balances on many cores, and they have great algorithms for query decorrelation and window functions, and all this stuff is also in DuckDB. And that's performance, but actually performance is not the main thing. Why is DuckDB popular? Because it's easy to use. Ease of use is actually also an underrated, and I'm telling this always to everybody here, we're always working and focusing on performance, but ease of use is more important often, because if something doesn't work and users are struggling with your system, they may be struggling for days or weeks trying to get something done. And that's actually those days and weeks, if you count them in your query performance, that would be really terrible. So actually making the user getting to a solution is what we should be optimizing, not only the query time. Okay, so that is a common theme in DuckDB, and I think that explains why it is so incredibly popular. DuckDB's web pages used to be by far, by a factor 100, the most read web pages in the CWI website. Now they have an independent website. Well, they have downloads that they can't pay, so they put them on Cloudflare because it's like terabytes per month. They have millions of users, so this is by far the most successful CWI system ever. Okay, so there's all spin-offs. So I'm actually doing a sabbatical, not at DuckDB Labs, which is where Hannes and Mark are CEO and CTO, but at another company called MotherDuck, which is going to put, or which has put DuckDB in the cloud as a cloud service. Okay, duckdb.org, great stuff. It even runs in Wasm. There is actually shell.duckdb.org. If you type this now, you can demo how it actually runs in your browser. So yeah, okay. Well, lots of stuff to be said about DuckDB. Don't have time for it. DuckPGQ, that is the topic of this talk. Okay, that's the thing that Daniel has been working on a lot. We have been working on for a couple of years. What is it? It's a so-called DuckDB extension. So DuckDB is extensible. You can create extensions. So what does this extension offer? It actually extends the parser. So instead of just plain SQL, now DuckDB can speak SQL PGQ. I'm not going to explain that because Oscar did that. SQL PGQ plus some extensions. We can return paths. We can have some. Well, I will demo this. Some, and also of course some limitations. But I do think that this is probably the most functional PGQ implementation out there right now, and it has been kind of very silently launched. Maybe this presentation is the first time I'm talking about DuckPGQ in this kind of open voice, like it exists. It exists, okay? So you can actually go to something that's recently launched by DuckDB, which is community extensions, community-extensions.duckdb.org. Go there. It is actually something that DuckDB builds and distributes for recognized extensions that and they so when a new release comes, they will actually just also update this, and you can easily download this and find documentation about community extensions, because there are community extensions, but there are also core extensions. So DuckDB itself is has the basic functionality, and then DuckDB Labs also has a number of standard extension modules developed by DuckDB Labs itself, but these are ones developed by community, and we are community. They are now DuckDB Labs, we are CWI, so there's kind of a separation now between us, and also CWI is kind of a community group now. So what does DuckPGQ offer? So the new parser, the functionality. It also offers some UDF, so you can also do some graph analytics with it. There is some basic bindings for popular GNN libraries, graph neural networks, PyTorch, Geometric, and DGL. I will also talk in this talk about some progress work. So we are actually, that's not yet downloadable, but we are improving the pathfinding, and we are improving pattern matching. That's the last point, worst case optimal joins. This is well, I'm not going to explain this, but it's kind of more advanced technique that tends to work well on explosive joins, has been known from the theory community. We are trying to get this actually into mainline DuckDB, because we think it's not only used for DuckPGQ, but it could be useful for DuckDB at large. Maybe I should just try to, now I'm going to break something for sure. Yeah, so I see this? No, I have to move this window here. Does it work? Yeah. I need to move I can't really see my cursor. Am I there? Yeah. Click. Yeah. Okay. So that is DuckPGQ. The DuckPGQ website. I need to really stand a bit here. No. Oops. Okay. Yeah. So actually, the community extensions website. That's the one I said. It's this stuff. Then there is a. They talk about core extensions, but then I was mentioning community extensions. So you go here. Oh, sorry, this is the wrong. This is the GitHub of the community extensions. So I should click on list of community extensions here. Then you go here, then you see a number of extensions out there. DuckPGQ, that's what I'm talking about. And then you get here. So, and it says, okay, yeah, installing and loading. Now I'm going to do something even more dangerous. Yeah, here's my cursor. I'm going to also do a demo without any training. What can ever go wrong here? I should, yeah, it's behind this window now. I should somehow get this out of the way. Where is my window? Here's my window. Okay, so window, DuckDB. Suppose you already had installed DuckDB. It's not really difficult to do. I will increase the font size. Okay. Increase the font size. Hope it's readable. Okay, now you type something like install DuckPGQ from community. Okay. So you can do that on any, and then you do load DuckPGQ. That's all it takes, hopefully. So now I have, so it's really easy. If you already have DuckDB, you do this, and then you have DuckPGQ. You don't need to install it again after installing it once. So you just do load DuckPGQ for getting the functionality. And now, yeah, now actually this will have modified the parser. So now it understands yeah, this thing that Oscar was talking about. So you can create SQL tables or have SQL tables already maybe, and then you can create a property graph kind of view on this, saying, okay, this table is a vertex table and this other table is an edge table and all that. So I could tempt the demo gods by yeah, there was an error here. Well, okay, we'll make one more attempt here, but it should work. Can you hold this for me? With one hand, it's really going to be really difficult. I'm trying to get this. What's going on? Uh, what's I have to load tables first. Yeah, this. Oh, okay. It's a really clean implementation. This HTTPFS is a core extension of DuckDB. It offers support for reading from HTTP. Okay. Should have installed that before. Okay, so it worked. Okay, I have a property graph here. I did something. It produced some kind of result. So this is a query. So the from graph table. Okay, can do this. I can also do. Okay, this is a graph table query that looked for paths that had lengths between 1 and 3. I hope it's visible. You can also do things like plus or star. Actually, star means that 0 edges is also good. So this will change probably the outcome of this query. Well, I'm not going to go into this. You just see it, it works. It should work. Okay? So it should also be relatively easy to do. And I'll go back to the presentation, kind of. Oh, not really. I want also to show some of the website contents to highlight that. If you scroll down, actually, Daniel did a lot of work. There is here a link with DuckPGQ documentation. Yeah, that brings you to some kind of wiki. It's a Notion page. Let me make this bigger. Yeah, thank you. So here again, some getting started information for that. It's work in progress. Then here you get some more information on yeah, how to load, for instance. Okay, but loading information into this. This actually no longer. It was this outdated. Allow unsigned extensions. That's one of the advantages of the community extensions, that these are now signed as a protection mechanism. If you have your own extension, you need a cryptographically signed key that DuckDB gives to you, and only if you have that, you can do load without any checks. But now with this community extension, you can skip these steps. It has become easier. Navigating, I cannot see this. Where's my browser? Where's my browser? My browser is. Yeah, but the other window, the window that we were looking at, this one. Yeah, okay, that's all nice. There is something I want to show you about how you can some of the extensions that are in there. So I was saying, by the way, that yeah, you could see that there are paths were being returned. This is interesting, maybe. Yeah, this is about okay, more basic information, vertex tables, edge tables, okay, that stuff. Yeah, there is some support for inheritance. So if you load, normally when you say something is a vertex table, then you give it a label and you say, okay, this is called person and this is called friend, for instance, is an edge table. But actually in PGQ, things can get multiple labels in principle, not a single one. And certainly in DuckPGQ, you can have multiple labels. And you do that. So what we figured out is that we have an extension. So you can have an integer column, which we call a type mask. So in addition to being a person, you can, for instance, be a student or you can be an employee. And this is a really simple extension. So in this case, if the type mark is 1, I think you're a student. And if it's 2, then you are also an employee. So you have 64 bits. So you can have 64 labels. And you can give anybody multiple labels by specifying a mask. In the SMB, the LDVC and SMB, we have, for instance, messages, which are posts or comments. So then we use that to actually store a single table with all the messages, and the type mask tells whether this specific message is a post or a comment. And when we're loading this, so you can, this mask approach is basically flexible. One of the things you can do with it is inheritance. So you can give some people kind of multiple labels according to a hierarchy, but you do not even need to respect the hierarchy. You can basically assign 64 independent labels to any object with this. We found that a useful extension. So I think the main thing I wanted to say about extensions so far, plus the fact that we support returning paths, which I'm not sure if that is even already in the official standards. So we can do P is, and then the path expression, and then in P, what you will get in DuckDB eventually is a list of row IDs. DuckDB has row IDs. So every row in a table has a row ID. So you can actually also you can then go back to tables joining back on the row ID. And DuckDB also supports lists. So it has this, Postgres also has this. You can actually have structs and lists of structs. So you will get this result as a list of row IDs. That's a path in DuckPGQ. I think that should conclude with the demo exercise here. Let's try to go back now to. Yeah. Well, that was the labels. That was this mask. That can be, yeah. So messages could be posts or commands. Persons could be students or employees. Yeah. No. It's maybe more simple than I made it appear to be. Okay. Yeah. Let's quickly move on. I will actually now erase. Okay, we are going to erase. Okay, DuckDB queries, they go through the stages: parsing, binding, optimizing, executing. Most of that you can also extend. So extensions can create extra parsers. It's a kind of crazy story because the parser is only extensible in the sense that if a SQL query gives an error, then the extension parser is tried on the whole SQL string. So our parser is a complete superset. So it parses not only PGQ, but also the whole SQL, because PGQ is embedded in SQL. And we do that, we build this in a crazy way, because we actually have a forked DuckDB that has this parser. This forked DuckDB is what the extension module contains as symbols, and then our parser, because we don't really want to have an independent parser. We actually used we extended the Postgres parser in a fork of DuckDB, and then that's what we link in our extension module. So and then we rewrite this. This happens during the binding. So there is a syntax tree. We rewrite it, and a clean, normal logical algebra plan comes out, and that is then executed by DuckDB. Most of this was also described in the Cider paper that's there. Yeah, so it rewrites queries. So if you do matches, so pattern matching, it will basically rewrite those into joins. But what it also will do is, if you have, there are also UDFs, because it will do on-the-fly CSR creation. So every time you do a pathfinding operator, not matching, but pathfinding, plain matching is just joins. But if you do shortest path, then on the fly a CSR is created. It's actually also a rewrite exercise. Under the hood, there are UDFs that create this CSR. They are called UDF create edge, UDF create vertex. A rather complicated query is actually created under the hood for you when you do that, and this all happens. But at runtime, we actually create this CSR. So we don't need to maintain the CSR under updates, because every query is recreated from zero, which also has its costs, of course. But okay. And then this parallel pathfinding is done. Here, this is CSR. I'm not going to explain this. Everybody in the room knows this. And then there is this multi-source BFS algorithm that is a kind of scan-intensive algorithm that tries to do efficient pathfinding using parallel BFFs, and parallel actually in the sense that the SIMD instructions are used to evaluate multiple searches in parallel, up to 512 searches in parallel by using single instructions that actually do this. This is described in this The More the Merrier paper. Also TOM work, by the way, I'm not going to go into it, but it's a rather efficient way of doing pathfinding. And that is currently in this DuckPGQ, and that is what powers its pathfinding and path returning operations. The second thing here is, okay, now ongoing work. Ongoing work is my second point. So far what I've described is what you can just now use in the community extensions regarding DuckPGQ. We are not done yet. So we are trying to improve this. So this pathfinding had some problem, namely that it's not really parallel because it's parallelized on the work on the source destination pairs. And DuckDB is a morsel-driven execution engine. So you need a full morsel, which are 120,000 source and destination pairs for every thread. So only if you would be looking for millions of paths, you would actually get any parallelism. So that's not so good. So what we are now doing is fine-grained parallelism. And that means that even for a single source destination pair, we want to use parallelism. But in order to do that, you need you need a new pathfinding operator. So that is this new project. Ping and Ren worked on it. It is kind of complicated. I don't have much time. I have to explain two things: what he did and how DuckDB works. So in DuckDB, what this pathfinding operator is that it's a special one. Normally, an operator has a single source, a single input, and a single output. If it's a materializing operator, it's a sink. So it will force materialization for the input, and this could, for instance, happen in an order, the sorting operator. It needs to materialize the input, then it sorts it, and then it outputs it. This one actually materializes the input as well, but it has two inputs. One is the CSR, which is this data structure, which is created by these create edge, create vertex. So you will first kind of get the relevant part of the graph in there, create the CSR on it, and then it materializes all pairs. Okay, maybe you just have one pair, but you could also have a million pairs. So these are the pairs of nodes that you want to find paths between. Okay, you can also do some optimizations here. We are not fully there, because what you could do here is you could duplicate eliminate those pairs, because if your query asks you to repeatedly find the same pair, okay, you want to do it once. But even in BFS, if the source is the same, but you want different destinations, you can actually do it in one run. But because BFS will start as one source, but visit everything. So if you have multiple target destinations, you can do it in one run. So these optimizations are also not there in our current state yet, but our current state is in released anyway. And then this write part kicks in, which is the actual execution. And what that does is it schedules tasks So for every frontier, so this is BFS, so it's yeah, just go breadth first search, and every time the frontier is advanced by one edge for all the active nodes, this is parallelized. So there is vertex partitioning. So ranges of the graph are advanced by different cores, by different threads. And this is Morshow driven. So the threads will ask for ranges of the graph. They will advance any vertices and go to their edges, to their friends, ask for more work, and this cell load balances. So even within one frontier pass, there is kind of load balancing. And all of that is modeled in a DuckPGQ thing called events, because the finalize step, which is the method under which this runs, which finalizes the result, can actually have multiple events. This is something that DuckPGQ invented for multi-step merging. And then they were thinking, okay, if you are short merging, then you may need 5 or 6 events, because for every time you merge two inputs, you need some kind of new step where there is a barrier to wait for, and then you go to the next step. But here we are misusing the events, and for every frontier, we are actually generating an event. So we may be generating thousands, maybe even millions of events. So the first time DuckPGQ does that. Yeah, so this is, but it works. So somehow we kind of put the parallelism that we need, which is very different from the parallelism that the relational plan needs in DuckPGQ by doing all these things. The end result of this is that's parallel. I'm not going to share the results because they are too preliminary, but there is speed up, so this works better. However, we get into a sea of cache misses and synchronization, because if you do naive implementation of breadth first search, and different threads will visit the friends, which is could be any edge, and then update the status, then you need to synchronize. So you need to log in order to set the status of the newly visited friend from false to true. In order not to lose updates, you need to log that. And that actually causes a lot of overhead currently, because these cache lines get dirty. These booleans that you set from false to true, they are quite large. So they cause cache misses, and it's kind of not so good. So we are improving this currently in order to get better scalability. But it's ongoing work. Second ongoing work is, and Alton is here in the room, is on the way we do pattern matching. We do that with joins currently, so normal equi joins. So if you just have a fixed size pattern, we do that. We made a change in the DuckPGQ hash table, actually a bit inspired by this paper here. DuckPGQ uses bucket chained hashing for all joins. There was this 3D hash join paper. We were starting to think about this. What the change is that here you see a chain, and there are two keys that collide. A hash collision. It can happen in a hash table. So you have K1, K1, K2. But they hash on the same slot. And what we now do in DuckPGQ is actually we use linear hashing. So it's a combination of chaining and linear hashing. So K2 now goes to the next slot. So we have pure chains. So in the chains, there will never be key collisions. And these pure chains are kind of nice, because we can use them for, well, factorized query processing. Okay, but they are also faster, so they make DuckPGQ faster, and that's why this PR is merged. So this hash table, even just for DPCH, these are DPCH queries, improved the DuckPGQ performance. It was merged, so we got this in. We were happy with it, but for us it was just a stepping stone. And then, yeah, we are kind of getting to similar ideas as Alton, who just published here in VLDB this very nice paper, which I all recommend you heartily to read, the Diamond Hardened Joins paper. It is my tip for the 10-year Best Paper Award for 2034. Not sure, of course, we'll have to see, but I think it changes a lot of things in query optimization, in factorized query processing, in worst case optimal joins. It kind of gives all kinds of new possibilities, and yeah, we kind of simultaneously co-discovered some work. We were doing it maybe in a slightly more hacky implementation, different way, but I'll try to give you the intuition. We're talking about cyclical joins here. The smallest cycle is a triangle. So here we see an example of a triangle query. In DuckPGQ, in a triangle query, you get not 3 joins, but you get 2 joins. How does that work? First, you go joining friends with friends, let's say, or they're called here, what are they called? They're called follows. We join follows with follows, and then we join again. So after joining once, then you have like you have a triangle, but one edge is missing. And then to close it, you actually have a double join that touches on both ends. So this is the join plan that's the most sane join plan. You would not do a triangle join in 3 joins. You always do it in 2 joins because it's possible. And the closing join typically has a double key because it's actually closing the cycle. So it has, you can build a hash join on a combined key actually of two node identifiers. So this is a normal join plan that you would get from DuckDB on triangle join. Now, if you do an end-to-end join, which follows it will generate multiple results. Then what you here see is that that you actually get multiple hits. So one source tuple in a normal end-to-end join can produce, in this case, 2 result tuples. You could have done this differently because there were 2 hits, in this case, Alice and Bob. You could actually say, okay, I will emit a list. Okay, I could make a list object. In the theoreticians would call that an F representation. You are not blowing up, but rather than emitting 2 result tuples, you actually emit a single tuple, but with a list in it. But there is also something called D representations in theory talk, which means that you actually point to the definition. And the nice thing about pointing to the definition is if you have the list Alice and Bob multiple times, you will be pointing to the same object in memory. So D are called because they point to the definition. In our case now, we have the ability to point to these chains. So we actually emit a pointer right into the hash table. Okay, we call this a chain pointer. That's why we have this kind of pointer there. So, and that pointer is actually the same pointer if you have the same hit. So you do not copy anything there. So that's a chain pointer. And then, okay, so what eventually happens, so here you see the same triangle join again. This is the original plan where you have, in the second join, you have a combined key, A and B in this case. What you now get is you get now these hash tables where, we have chain pointers. And the second one, you would change them to a single column join that therefore will give you not only a single hit, but actually a chain of hits. The B's is now a list of B's. And effectively, the first join gives us a chain. The second join gives us a chain. If you intersect the chains, then you find the final result. In order to find the final result, you need to intersect the chains. If you do that in a fast way, as fast as the shortest, then you get a worst case optimal join. That's also an idea in Altan's paper. But what we do is we actually do this adaptively. So when this is join that actually is one join pipeline that does 2 joins after each other in one pipeline. But before that pipeline runs, the builds have built, which are the separate pipelines, they build the hash tables. So during the build of the hash tables, we already get to see all the data. And that means that we could construct sketches on this data. Because one of the problems in DuckDB is that very often we don't have statistics. So we don't even know what the foreign key and the primary key is very often in DuckDB. So if you join Parquet files, for instance, nobody will tell you. But in runtime now, we can discover some interesting statistics. We have these 2 sketches, HLLs and AMS. And this is triggered by a cyclical query. So a cyclical query triggers the creation of these sketches. And then when this final join pipeline starts running, we have these sketches and we can make a decision whether we actually want to change into an intersection strategy. Okay, and we build some kind of model that based on the features from the sketches predicts whether worst case optimal join is beneficial. Because actually the big problem with worst case optimal joins is not only implementing them fast, but also knowing when they are better, because they are not always better. They are sometimes also slower. This is our bit in doing that. There is a submitted paper out there. We know, who knows what will happen to it. Hopefully it will be accepted by the reviewers. So yeah, this is actually as much as I can tell you currently. But that's my conclusion. So DuckPGQ is out there. It's kind of maybe a first attempt at releasing this or announcing this. It's an extension, a community extension, so it's really easy to get to. It has basic support for DuckPGQ. We are really eager for your feedback. I think it's kind of nice maybe for PGQ that there is implementation for it in a popular database system. And there is ongoing work. I talked about making the pathfinding parallelism better and about this factorized query processing. We don't actually know where and how this will land. Maybe it will never land in DuckDB. I hope it will land in DuckDB. The best would be that it would land in mainline DuckDB because it's not really something that is specific to PGQ. Any big join with exploding joins could benefit from this. But well, okay, landing PRs in DuckDB, okay, we don't know whether that's actually going to succeed. So maybe it will first be only in DuckPGQ, but it's not even there yet. But it's ongoing work, and that's what Daniel has been up to together with Pingyan and Paul, who, by the way, Paul is also joining the CWI as a PhD student in the future. Thanks for your attention.
Hi there, Xiang from Waterloo. I'm a huge fan of DuckDB. I started following DuckDB since 2020. So I have two questions. So first, for the new parallelism for this pathfinding algorithm, as I understand, if you get 10 threads, one source destination pairs, you're still able to parallelize it with this new.
Yeah, because it's a separate path, but that schedules tasks and all that. Yes.
Yeah, and my following up question is: suppose you get 10 source destination pairs and you get 10 threads. How would you do this scheduling instead? Were you trying to?
No, not instead. It's exactly the same. So that would not change it in a bit.
So you mean threads will? There are different strategies. You can.
No, the parallelization is on the vertices, so it's on the graph. So different areas of the graph the frontier will be advanced by different threads. It doesn't matter how many source destinations pairs there are now. You parallelize on the graph.
Okay.
You need you need a non-extremely tiny graph, but if you have like millions of edges, then it will already parallelize pretty well.
I see. Okay.
I think for the SIMD approach, as soon as you have fewer than 512 pairs, you will have less benefit from the SIMD because the SIMD can do 512 searches in SIMD parallel as well. So okay.
I see.
Yeah.
Oh, okay. So I have another question about this factorized hash table. So in the factorized hash table, you're able to keep certain columns as list, and you do the worst case optimum join afterwards. When you output from worst case optimum join, are you able to still keep the factorized form, or you have to output in flat form?
We currently output in flat form. So our approach, I mean, in the paper by Altan, he is kind of proposing to split joins into two phases. One is the lookup that will actually give you the chain pointer, and then the expand, which will expand this. In our view, we try not to implement expand. We kind of basically trigger this currently only in situations where we can avoid expand, which is exactly what factorized query processing with FA would do. So this also, by the way, there's also ongoing work on using this in aggregations. So, but the idea of a cyclical worst case optimal join is that just like an aggregation, it is a step that will make the result, the intermediate result, really small. Like the idea of the diamond hardened, diamond queries are queries where the input and the output is small, but the intermediate is large. And the idea of diamond hardened joins is to trigger optimizations that attack this very large intermediate results. So, but we are going even further in that sense that we are even more opportunistic, and we'll only do this if we can really avoid the expand completely.
I see. Yeah, I assume if you do aggregation, you can also do early projection, keeping the multiplicity of the list only.
Yeah.
Okay, thanks.
Okay.
Yeah, thanks for the great talk, Peter. So my question is on GQ. So how do you view the relationship between PGQ and GQL? And will DuckDB support GQ by extending all your clone technologies to GQ?
I'm looking forward to your PR.
Yeah, I know.
Yeah, yeah. Or pay me.
I see.
Somebody will do it, maybe. I mean, it's easy enough in DuckDB. I mean, it's likely that somebody will use DuckDB for analytical purposes. So, yeah, maybe you, maybe somebody else. Yeah.
Oh, sorry, Peter. Just a quick question because you said you built a graph on the fly. That means that you construct all the CSR data structure on the fly while
Yes,
querying.
yes. We do.
Yeah, but that's costly if we're dealing with a large amount of work.
No, well, not less than you think. So, I mean, we only do that if there is pathfinding ongoing. Tends to be the case that pathfinding is an expensive operation. So, if you look at the performance distribution or the time distribution, then in the cases where we use this, pathfinding tends to be 10% or 5% or 1% or less. So, depending on how many paths you're finding.
Okay, but that determined on the query itself. So
yeah.
Is there a way to determine whether building this graph is you can save something, or compared to the query? For example, we can do statistics on the path.
Currently, it's a very simple heuristic. So if there is shortest path finding or connectivity query with a clean star or of some kind, then really unlimited clean star,
sure,
then we go for it. You can of course ask yourself, okay, what if you want two-step, if it's nose 2 or nose 1 to 3 or nose 1 to 4, where is the limit where switching over to this might be beneficial? Currently, we do anything with variable amount of, but well, that's actually a debatable choice. So I think we should not indeed build a CSR immediately. Only on significantly long paths it will pay off. But there is currently no good heuristic for that. So that's indeed something to think about. Actually, the whole idea of using a CSR is also debatable, because what we are so there are also people like Dennis here, and they're also working with Torsten Gruus. They're also working with DuckDB. They argue that you should do this pathfinding with recursive queries, actually. Yeah. But then you would actually have to do hash joins, hash lookups, and the CSR in a way is potentially faster, or it should be faster because it's a really dense data structure. So yeah, but for the complexity of the system, it might be better to do actually everything with the DuckDB hash table. But we figured that something like the pathfinding algorithms, the more the merrier. Yeah, it works really well if you have the CSR.
So have you considered like cheaper method, like Semi have introduced
no.
No,
no, we only optimize things that are really a problem. So this we don't consider as a problem yet, because it doesn't show up as a problem in profiling.
Okay, sure. Thank you.
But there is lots of stuff like long paths, returning paths, that are problems, but that we should address those first.
Yeah. Any pattern matching could have that issue
as
well. Thank you.
Yeah. I think it's lunch. We are very late, probably. But I started late as well. But I made it worse. I think I did make it worse. Sorry about that.
It's okay. So